Good morning guys, and welcome to today's worked exam answer video. Today I'm tackling another calculation question in the main because these videos seem to be incredibly popular, which probably reflects the fact that calculations are less popular. But in today's question we're doing a little bit of reacting masses as well as doing a bit of PV as NRT, and then we've also got some suggest questions at the end, where suggest questions are a chance for us to show what we know. They can be quite tricky because we kind of got to use what we've been given in the question and sort of use our own knowledge and kind of make a bit of an educated guess. I think these two are fairly okay to answer, but obviously if you disagree once I've gone through them, then please do let me know. So in this question, we have got some iron 3 nitrate, and we've been given the MR of that, which is quite nice because it's quite a lot going on there. So 241.8, and that iron 3 nitrate is converted into iron oxide, nitrogen dioxide and oxygen. It then says that we start with a 2.16 gram sample of iron 3 nitrate, and that was completely converted into the product shown. And the first thing we've got to do is calculate the amount in moles of iron 3 nitrate in that 2.16 gram sample and give our answer to 3 significant figures. Now I like this question because they've kind of broken the 3 steps of this calculation down, whereas they very easily could have kind of put A or I, and III, all of part A into one, which will have been a little bit more daunting. So hopefully seeing it broken down like this will help for those times where it is all put together. So moles is equal to mass divided by MR. Now, I'm not going to lie, first time I read this question, I skim read the top part and didn't see that they'd given us the MR. So I worked it out. So top tip, don't skim read the early parts of the question. Make sure you read all of it, because you might end up doing more work than you need to or missing something that's really important. So 2.16 grams divided by the MR of 241.8. It's going to give me my moles, and I need to give it to 3 significant figures. So you can write your full answer down first, so I'll do that. So 8.933, so on and so on. Don't need to go any further than that. Times 10 to the minus 3. And then make sure that you then write that to 3 significant figures. Now, doing this in standard form is absolutely fine. You can give it in non-standard form if you prefer. Either's fine as long as it's 3 significant figures. So my final answer is going to be 8.93 times 10 to the minus 3. I'm just going to make that clear that I've done that one to 3 significant figures like that. Okay, so that is our moles of the iron nitrate in our equation. Now in the next question, we have to calculate the amount in moles of oxygen gas produced in this reaction. So the oxygen gas is one of our products. What I should have really done before is highlighted in the equation my iron nitrate, like that. In terms of working out the moles here, we don't have any information about the oxygen. The only thing we have is the moles of the iron nitrate that we've just worked out and our balanced chemical equation. But that is enough, because what we're going to need to do is have a look at the ratio between the iron nitrate that we have the moles for and the oxygen. And the ratio is 4 to 3. Therefore, there's a few different ways you can do this. You can look for how we go from 4 to 3 in terms of what we divide 4 by to get to 3, and then divide the moles by that. Or for someone like me who likes to do the maths in the most simple way possible, I'm going to take the moles I had here and I'm going to divide it by 4 to get one part, and then I'm going to times it by 3 to get the 3 parts for our oxygen. So doing it like, trying to think. I swear I used to do this in like GCSE maths for ratios or proportions or something like that. Always find one part and then scale it back up again. I do the same for percentages as well. So yeah, I'm going to take my 8.93 times 10 to the minus 3, and I'm going to first of all divide that by 4 to give me 1 part, and then I'm going to times it by 3. And when I do that, I get 6.6975. Now, because we've used 3 significant figures for the moles of the iron nitrate, I can't now give an answer that's more precise than 3 significant figures, because you can't be more precise than your least precise bit of data. So giving that to 3 significant figures, 6.6975 is going to be 6.70 times 10 to the minus 3. And for all calculations, we should be looking at the values that we've been given in the question and matching the significant figures. Obviously, if we're told something different, go with that, but we weren't. We were given 3 significant figures as the clue in part I. The mass was to 3 sig fig, the MR is to 4 sig fig, because MR is always to 1 dp, and we'd always use the lowest of those 2 precisions, which is 3. We gave it to 3, and now we're sticking with 3. Okay. Now that was getting you to grips with using the ratio. What we're going to be doing now is something similar, but not involving the oxygen. We're going to be involving the nitrogen dioxide, and they've put that in bold to make sure we're clear that that's what we're working with. The nitrogen oxide is there in our balanced chemical equation, and we have to calculate the volume in meters cubed of nitrogen dioxide gas at 293 degrees and 100 kilopascals that can be produced from the 2.16 grams of iron 3 nitrate. So that's just telling us that we're still using the number of moles of the iron nitrate that we worked out in part I. And we also know that because it goes on to say, if you've been able to obtain an answer in part I, then please use this number. And AQA are really good at that, because they don't want you to then be penalised further. If you can't work out the moles in part I, then you would also lose these 4 marks if they didn't give you a value to use. So that's nice. And then we've been given the gas constant. And if we need the gas constant, it will always be given to us. And what hopefully our brains are thinking right now is we need a volume, we've got a temperature, we've got a pressure, we've got the gas constant, and we can use our equation to get moles. So we should be thinking PV is nRT and nitrogen dioxide is a gas, which is helpful. So that's the ideal gas equation. And then if we want volume, we're going to rearrange that to get volume is equal to moles, gas constant, temperature, times together, divide that by our pressure. Now for ideal gas, the volume will come out in meters cubed, so we do not need to convert our final answer, which is nice. But we are going to have to convert our temperature, because temperature should be in Kelvin. So I'm going to have to add 273 to the temperature we were given in degrees, which gives me 566 Kelvin. And I also need my pressure to be in pascals, not kilopascals. So I need to times that by 1,000, and that will give me, oh, I've done that wrong, haven't I? Put my comma in the wrong place. 100 times 1,000. 1, 2, 3. Yes, I have. 1, 2, 3, 4, 5. There we go. Nice little fix there. I just like having the commas in, but yeah, maths in my head, again, not my forte. So the thing that we don't have is the moles, but the thing we can get, again, using the balanced chemical equation, is the moles. So again, if we're thinking about the ratio, we've got this time iron nitrate. We need to think about the ratio of that to the NO2. we've got 4 to 12. So the moles that we got in part I, the 8.93 times 10 to the minus 3, I'm going to need to times that by 3 to get the moles of the NO2. .93 times 10 to the minus 3 times 3. Again, I could divide by 4 and times by 12, which is kind of what I did here, but I think looking at how to go from 4 to 12, it's easy enough for us to see that we need to times by 3, because 4 times 3 is 12. But if you can't see that, always divide by whatever this number is to get one part, and then times it up accordingly. That gives me a number of moles of 0.2679. So that's going to be 268 to 3 sig fig. I'm going to stick with the trend. And now we've got everything we need to get volume. So the volume of the NO2 is going to be moles, 0.0268 times the gas constant, 8.31 times the temperature in Kelvin, 566, divided by pressure. So 1, 0, 0, 0, 0, 0. So 100,000 pascals. And then I just need to put that into my calculator to get my answer. So 0.0268 times 8.31 times 566 over 100,000 equals 1.26 times 10 to the minus 3 meters cubed. And again, that's me giving that to 3 significant figures, following the trend throughout. You can again give it to non-standard form if you prefer, but that is also acceptable, and that's what my calculator naturally gives my answer in, so that's what I'm going to choose to leave it in, rather than making life a little bit harder for myself when I don't need to. So here you're going to get a mark for converting the temperature and pressure, so that's 1 mark for those 2 numbers there. Another mark for working out the moles using the ratio of the NO2, and then another mark for rearranging the PV as nRT equation and either rewriting it like this or rewriting it like this with the numbers subbed in, and then 1 mark for our answer. Happy days. Okay, then we've got our 2 suggest questions. So it says suggest a name for the type of reaction that iron 3 nitrate undergoes. Now the first sentence says, when heated, iron 3 nitrate is converted into those 3 things. We haven't got another reactant, it's just the iron nitrate, which then turns into those 3 things. So it has to be breaking down, and we're heating it to do that. So thermal decomposition. The mark scheme is actually only really interested in the decomposition, but I do think the fact that we're heating the iron nitrate is a clue. So I'm going to go with thermal decomposition, but yeah, we're not adding anything to the iron nitrate, it is just breaking down into those 3 products. So as far as suggest question goes, I don't think that's too bad. Likewise in part C, suggest why the iron 3 oxide obtained is pure. Now you might be thinking, oh, because the reaction's complete. Unfortunately, they've made this a little bit harder by saying we have to assume that there is a complete reaction. So one of the reasons why we might not get pure iron oxide is because some of this might not have decomposed. So then we've got a mixture of these 2 solids, which obviously means that this is not going to be pure. But if we're assuming a complete reaction, all of the 2.16 grams of the iron 3 nitrate has decomposed, and the solid that we've got is the iron oxide, that would then be pure. What we can also look at though is the other products that we've made. So we've made a solid and we've made 2 gases. These gases are not going to make this solid impure, because these gases are probably just going to be allowed to escape. We don't if we're not wanting to make iron oxide, if we're only wanting to make the iron oxide and we're not trying to make these gases, then they can just leave. But even if we are wanting to make those gases, they're not going to mix in with the solid and make that impure. So it's a case of looking at what we've got for state symbols for our products. If we had multiple solids being made, then those solids would mix together and it'd be really hard to separate them. If we had a solid and some liquids, it'd be a little bit easier. If the solid was insoluble, we could then filter it out. But yeah, this is ideal because the gases are not going to contaminate the solid in any way. So suggest why the iron 3 oxide obtained is pure. The other 2 products are gases. And there we have it. So that came from an AQA AS paper, a bit of an older paper, but still very relevant in terms of the content of this question. As I said, you might be asked to do sort of part I and part II certainly all in one, which might make it seem a little bit more complicated than this one, but it would be the same skill set that you'd be using, so hopefully it helps to see it laid out this way. Any queries though, please do not hesitate to get in touch, and I hope you have a really lovely day. Thanks for watching. Bye.